Hi Shafi, welcome to India. Thank you for agreeing for this fireside chat on behalf of ACM. So I want to start by introducing you a little bit. Our audience don't need introduction for you, but I just want to say, we can't talk about any topic in modern cryptography without referring to Shafi's work. Not surprisingly, she won the Turing Award along with Silvio Micali for their foundational contributions. Currently, she is the director of Simons Institute at Berkeley. I can go on giving a long list of her achievements and awards, but I would rather spend that time listening to her talk rather than give a long bio. So with that, Shafi, let's begin.
First, I'd like to say thank you for inviting me. I'm extremely honored. This is my third visit in India, and I think second visit in Bangalore, and I'm thrilled to be here.
Thank you. Okay, yeah, Shafi, you're an awesome inspiration for all of us, and I want to ask, what was your inspiration, or who were your role models? What shaped your interest in math and crypto and your research career, such an astonishing research career?
I guess my first role model was not a mathematician or computer scientist or even a scientist of any sort, but it was my father. And the inspiration was that he was very convinced that his children were destined to greatness, which was in our eyes ridiculous. But he was like, oh yes, my children are the best, and so forth. And in particular with me, he was extremely encouraging, some may say pushy, that I should go to the States and study. And I went to Carnegie Mellon as an undergraduate. And when I was an undergraduate in Carnegie Mellon, at the end of the undergraduate, which was wonderful, I sort of realized that I knew nothing, or I didn't know enough, and I wanted to specialize and to learn something so that I'm the only one who knows this topic better than anyone in the world. There's at least one topic that I'm an expert in. So I went to UC Berkeley for graduate school, and there I actually, to begin with, wanted to do AI, but I ran into the theory folks, the theory graduate students, and they seemed to be such an interesting bunch. They were from all over the world. Sylvia was from Italy, and Vijay Vazirani was from India, I think from Delhi. And then there was Mike Luby from Denver, and they were so passionate about what they were doing. And I took some theory classes also. I decided, you know what, I'll do theory. So Berkeley was extremely strong in theory in those days, and there were really very few people doing AI. Today, I think Berkeley is also very good at machine learning and AI. But in any case, the true inspiration was a course that I took from Manuel Blum, who was my advisor, and it was a course on computational number theory, which is essentially take problems in number theory, like the most elementary problem is a number a prime or a composite, and then how to factor numbers, how to take discrete logs, how to generate, come up with generators for finite groups and so forth. And from an algorithmic point of view, that is not just show that there exists a factorization or there exists a proof, but find it. And at the end of the course, he had 2 lectures. And in that 2 lectures, he described what modern cryptography was at that time. He didn't call it modern cryptography. There were 2 papers. Yes. There was the Diffie-Hellman paper about public key cryptography, and the RSA paper, and maybe there was one more paper about breaking a scheme. And it was fascinating. And that was really my inspiration to do cryptography.
Okay, that's fantastic. Yeah. Great.
Long answer to a quick question.
It's good. It's good to it's good to learn the history, and it's good to know what inspires great people. Yes. So switching gears a little bit, one of the interesting things that we see in India, in the Indian academia actually, is there is a very good representation of women faculty in cryptography. But this is not true in the larger geography of India, just like everywhere else. And it's definitely not true in STEM fields, like broader STEM fields. Yeah. Cryptography is really an exception. Yeah. Some of the institutes in India actually have as high as 75% of faculty being women in cryptography. So I wanted to ask your advice, what could academic institutes in India do, or anywhere else do, to encourage more diverse research faculty, researchers, in cryptography and broadly in STEM fields?
So I guess more diverse in cryptography means getting more men. But so first of all, I guess it's true also in the States. Yeah. They're very strong women in cryptography. At MIT specifically, my former student, Yael Kalai, she's
our colleague, yes.
She's now a colleague. She used to be a student. She's there, and I know that now in the group in MIT, where which are being headed by Vinod, by Nathan and Yael, because I've moved to Berkeley, the graduate students there's certainly something like 80% women this last few years, and they're writing papers like crazy. So these are not just that there are women there, but they're doing extremely good work. So what you mentioned about having women in the field, it's not just that there are women in the field, but they're doing really, not just very well, top of the line, the best research out there. There's also Rachel Lynn that did the work on obfuscation with actually Amit Sahai from UCLA, which are sort of the runner-up results. So why? Why are there so many women in that? How can we learn from that to export this to other fields? I think to some extent I probably should take credit for it. It's not that I mentored all these women, but I mentored some of them.
Role models, yes, yeah.
Actually, when I was younger, people used to talk about ask me this question: who are your role models? And I couldn't answer because I think that women traditionally don't think of role models the same as men do. Because maybe there are not that many that are similar to them. There would be role models. But I do think that role models are important. So I think that having somebody like me, maybe Tal Rabin a few years afterwards, and then Yael, and others, extremely important for the field. Now in machine learning, I think that, at least at MIT, there are a lot of women. There were no people in machine learning. I think there was one faculty member, and then all of a sudden they hired, in the last 6 years, everybody just wants to hire more and more machine learning people. Maybe too many, but whatever. Maybe you could scratch that. But because it's so quick, how do we know where it's going? But in any case, there are women. There are a lot of women. A lot of them come out of Berkeley. I think from Michael Jordan's group, there are a lot of postdocs, faculty. What to do? I think it's extremely important for the male faculty members in other fields to mentor women graduate students and not to assume, which I think they used to at least, and they probably still do, that the women are there, but their opinion maybe counts a little less than the male graduate students. So you have a group, usually these days, right? The groups are not small. In a group there might be some men, some women, maybe there's less women, most likely, and you talk about a topic. Traditionally, I think culturally, the men are more assertive about what they think, and they're more convinced that what they say is true. The women less so, and perhaps the advisors as well. So I think giving a voice and listening and is incredibly empowering. I think early on, often when you have a graduate student, in their first paper they might join into an existing project, and then often faculty have to make a choice of which student to invite to a project. Then they might make the choice based on not really merit, because they don't know much about entering graduate students. You do it for women and men equally, even in the important projects. Because once you have a paper, which you may have not conceived entirely on your own, you have gone through the process of being able to write a paper. And then you know that it's doable. So I think all these steps are extremely important when people are mentoring. And they have to suspend this belief about whether this is there's always in a group of students, you say, this is the star. He's a star student. Very bad mentoring. I have tried not to do that. Conscientiously, always.
Exactly.
And people, the one thing I can tell from many years in academia, the wonderful thing about academia is it's always young people. I mean, by the time you're my age, it's not so wonderful because you realize there's always young people younger than you. But it is wonderful because there's always new talent, there's creativity, and you really cannot predict in advance what people are going to do. And when you believe that and you suspend this belief about your priors, about whether women can do as well as men, and then the students believe it as well and they'll do well.
Thank you. I think this is good advice for all of us.
And I must say that Ron Rivest, who was kind of a mentor to me, although not in official capacity, when I moved to MIT, like in 1983, he I had a postdoc there, and then I became a faculty member. And he was around. And the thing about Ron is that he has always had a lot of women graduate students, but I wasn't his graduate student, I was a colleague. But there was something about him that he was very interested in new ideas, and I felt completely listened to.
That's good.
And I do think that it's an individual thing. I don't think a collective can do anything. I mean, you can make plans, you can have programs, that's not it.
Okay.
Yeah.
Right. So let's now talk a little bit about cryptography. Of course, over the last couple of decades, there's tremendous progress in every subfield of cryptography, and you have made seminal contributions to pretty much everything, like FHE, obfuscation, MPC, ZK snarks, and so on. Is there a favorite topic that you want to talk about in those established or like relatively more established areas? And also, could you tell us a little bit about how you are leading new activities in cryptography, especially related to some of the applications that cryptography might have for societal problems at Simons?
Okay, that's a big question, so it's going to spans a few topics.
Yeah.
So in terms of my favorite of the past topics that I've worked on within cryptography, it's because I've done work also outside of cryptography.
Yes.
I think that every few years, maybe it's every decade, and some decades are more packed than others, there's sort of a new idea. And originally, of course, there was public key cryptography, but when I came on the scene, I think the focus was, how do you, let's say, encrypt a single bit using probabilistic methods? How do you define security just beyond just not being able to recover a message that has been encrypted from the encryption, but how do you hide all partial information about it? And that was, and this idea of using probabilistic methods, of thinking of things, of security, really in a much more deeper way, like defining partial information security, and how do you actually get that by looking at the binary representation of messages. That was fascinating. And it made its way from encryption to digital signatures. How do you really sign binary strings in a way that you can't forge and come up with another, even a small perturbation of signature of it, and so forth. And then a decade later, there was multi-party computation. That is, how do you not just encrypt, but how do you compute in a collaborative manner when there's a few people and they come together in order to do a computation without giving each other their individual data. But the computation depends on all the data. And again, you had to define, what does it mean that you don't find out information about other people's data? You want to define in a very strong way, that you cannot find anything more than what the output of the computation dictates. So that was sort of, again, a whole slew of fascinating, because there was a core idea. How do you actually collaborate? And then, there was FHE. So these are jumps, right, in time, where fully homomorphic encryption, where you don't need to interact at all, and you can just give someone encrypted messages and an evaluation key, and that enables them to compute functions, programs on the underlying plain text without decrypting. So to answer your question, what's my favorite? I think my favorite is a result that has a new tool, a new idea, because it's actually kind of staggering what you can do. And zero-knowledge proofs were another example. Like you don't want to hide it. It's not like you're transferring information. You want to sort of prove that something is true or false, let's say true, without giving any inclination of that without transferring the ability for you to prove to someone else that it's true. Like proving, let's say, that if you think about modern application, maybe I can prove that I am a citizen of EU, European Union, without saying which country, and that I'm of age, and that so therefore I'm allowed to, I don't know, maybe drink alcohol, consume some substance without telling my exact age. So I can prove my legitimacy without giving a lot of other details. And zero knowledge enables you to do that. Of course, when we came up with zero knowledge in the 80s, there were no digital IDs. There was no notion of using this in practice. It was just, but the idea, the grain of idea of how could it be even possible that I will convince you of a fact without giving you everything else, it required an understanding of what interaction and randomness are beneficial for, and how they can enable this. And then later you remove the interaction and have these non-interactive proofs. All this to say that from the past, it's hard for me to say that there's one favorite. But the favorite is when there's something really new. Of course, you need a whole body of work to make something useful. You need to make it more efficient. You need to polish it. You need to understand what's essential and what's not essential. To me, the most kind of interesting thing is if somebody can explain to you what it is that made this thing all of a sudden go from impossible to possible, I find it fascinating. And cryptography is full of that. I think that's what makes cryptography maybe a little different than a lot of other areas in theory.
Yeah, a lot of paradoxical sounding constructs.
That's right. That's right. And then there's an idea, there's a technical idea. They say, wow.
Yes.
Yeah. Now your question had a lot more components to it. You have to remind me.
Yeah, that's fine. Yeah. So, yeah, I was also asking, some of the new activities of applying cryptography to some of the societal problems that you are leading at the Simons Institute.
Yeah. So let me tell you about the societal implications of some of the old cryptography, and then we'll talk about Simons, the separate things. So in terms of, so because cryptography is really a success story, I know it's not humble to say, but it is a success story, at least on paper. And it's also making its way into, it's clear that there's something here that involves mathematics, and sometimes not even trivial, which enables something that seems paradoxical. And now with the new data revolution, where we've got all this data out there and we're trying to milk it for a good reason, for better infrastructure, for better medicine, right, for better energy usage, for better policing, for better security. It also means that there's a lot of switch of power. So in some sense, whoever holds the data control
a lot of power.
A lot of power. And the question is, how do you make sure that that power is not abused, and that seems to imply that you have to maintain privacy. And in fact, regulations call for it in different countries. There are different rules. I don't know what the rules are in India, but certainly in Europe,
it's coming. Data privacy laws.
That's right. So in California, there's the California Privacy Act, and in Europe, there's the GDPR. So there's privacy. There's, in some sense, safety. So to prove when there's a big machine learning model, say, and you want to verify properties. So is it really accurate? Is it fair? Is it robust? How do you prove it? Say you are a trainer that you've come up with a model and say, use my model in court, use my model for infrastructure, use my model for even for medical application. Why should you trust it? Correct. So you need some mechanism to verify. And if you think about what I talked about before, about verifying the properties of your ID, again, there's underlying it, there's a mechanism for verifying claims. And the claim there might be that the machine learning model is delivering what it's supposed to be delivering. So I think cryptography society is going to be controlled by these big data-driven automated systems. Then making sure that it's done properly, it will have direct societal implications. Now there are shorter-term things, which are things like that were used already in the U.S. Census. So in the U.S., every 10 years, there's a census. They're sent to everybody, and people are supposed to say how many people live in their household, what's the average salary, and some other data. And all this is collected and tallied, and this is used to later understand which resources the federal government is going to give to different areas, depending on the density of population, the average salary, and so forth. So you to sort of trust that people give you the right information. On the other hand, they're also holding now all this information, and that's why people don't give the right information. So let's say there's illegal immigrants that live in a certain area, and they don't want to reveal it. And yet now the area is not going to get resources, but you can understand the tension between revealing and getting back resources. So the U.S. Census Office decided for the census that happened a couple of years ago, to use differential privacy, which is a method to enable people to give in data, but then when you collect it in such a way that you can't find out anything about an individual entry, but you do get a good signal about the majority, or about the tally of the data. And that's a direct use of some cryptographic method, which is called differential privacy, to a societal problem, which is how are you going to make sure that redistricting is done in the U.S. How do you make sure at the same time that people answer questions honestly, but their privacy is not threatened? Having said that, it's being challenged broadly in the U.S. because some regions that don't like the answers of the census claim that this is a statistical method. It can have errors, and that means that perhaps some area should get resources is not going to get resources because of the errors in the method. So making changes in society is not so fast, and maybe it's good. I'm just saying that there is a cryptographic arsenal of tools.
Yeah.
It does clearly have use in society, but it's going to take time.
Yeah.
It's already remarkable that it was used.
Yes. Yes.
Yeah.
Great. Yeah. Thank you. Now, we have been talking about a lot of foundational advances in cryptography and how it impacted society, or it is impacting society. But there is still this perception, especially in some of the applied areas of computer science, about the wide gap that needs to be bridged between theory and practice. How do you think about, from cryptography perspective, how do you think about this gap between theory and practice, and what's your guidance on how the future generations could bridge this gap or keep continuing to bridge the gap?
So I think that's a great question, because you see that cryptography, really there's a big lag between things that seem to be so fundamentally useful and the actual use in practice. So even, public key cryptography, just the RSA, digital signatures, it took time. If you talk to people who were in the RSA company, it took some long time and effort for this to be accepted as a standard, for getting a patent, for this being adopted. And certainly it's the case with zero-knowledge proofs. When we came up with this in the early 80s. Yes. The first paper, I think, was published in 85. The ideas are from 83, maybe. But now, everywhere I go, I go to some wedding, and some distant relatives of some of the guests, they know about zero-knowledge. And they know about zero-knowledge because blockchains, Right. So who would have thought, right? And that's practice. Yes. So the lag exists. Why does the lag exist? One is because, in some sense, privacy and cryptography are a luxury. In a sense, first you want utility, you want things to be run fast, and then you think about, wait a second, I want it to be done privately. So it's an extra benefit. And usually you take this extra benefit when it has some added value, because it won't be deployed otherwise, because there might be rules. There might be regulations, like in the medical profession. You have regulations, you're not supposed to send out medical data, right? But once you realize that aggregating a lot of medical data, like in genomics, clear that scale is everything. Yeah. The more DNA sequences you have, the more signal you're going to get to see what is related to what disease. Then you know that you need to get all this medical data together. Then you know that you must find some privacy rules or privacy methods to obey regulations so that medical data can be aggregated so that you can run your methods on it and get enough signal. So I think that the theory to practice is going to happen for cryptography when people realize they can't do it any other way. Yeah. Because I don't think there's really an inherent barrier. Mm-hmm. Right now, cryptography slows things down. So doing homomorphic encryption on data, like I have actually a company that I co-founded with Vinod, Duality Technologies, which does exactly that, takes fully homomorphic encryption and multi-party computation, applies it to finance problems, so problems in the banking system and problems in medicine in practice. So we build a system, we try to improve the kind of tests that people do, like logistic regression and, neural network training. But there's a slowdown, okay? So, but it takes time, it takes a lot of effort. It takes data scientists and cryptographers and people who understand deeply the mathematics involved. And so my sense is that the more it becomes clear that cryptography develops a value, adds a value, because there are regulations and you can't do without them, because there's something new that you didn't think even possible that you can do, the more people are going to put the resources needed to make it more efficient, and then it will be adopted. So that's the timeline. I hope. Because I hope Duality Technologies makes it big. No, but I also hope fundamentally, seeing your work put into practice, it must be wonderful for systems people to actually see the world run on technologies they've developed. And seeing this for cryptography is very satisfactory, but it does take time.
So looking a little bit into the future, depending on how far that future is quantum computing. So if we get quantum computers, several cryptographic constructs that we are using today will not be useful anymore, will not be secure anymore. So how well do you think we are prepared in cryptography to address security challenges in a post-quantum world?
So I actually think that in a post-quantum world, cryptography is doing better rather than worse. So it's true that kind of the big result that kind of propelled, I think, a lot of the interest in quantum computing, or maybe all of it, is certainly from an algorithmic point of view, was the result of Peter Shor, where he showed that factoring efficiently on a presumed to be built quantum computer is possible, right? And also discrete log and all the cryptography that we're using in the internet today.
Yeah.
However, at the same time, around like in the, I guess, late 80s, there's a paper by Aitai, Miklos Aitai, who for completely different, has nothing to do with quantum. He showed how to build some very simple system of cryptography based on a problem from lattice, integer lattices. And this was to show that there's this problem where you can show that the problem is hard in the worst case, it is in the average, which wasn't known for factoring. So it might be that some numbers are hard to factor, but not all numbers are. Here he showed that if there's some worst case problem on lattices, which is also hard on the average, which means that we can sort of pick an instance and use it for cryptographic purposes, and we know it's as hard as the worst case. Now it turned out that this method, then the subsequent paper was actually Cynthia Dwork and Aitai, and Cynthia Dwork is from Microsoft, and they showed publicly cryptography. But it turned out that he opened up a whole can of, not of worms, but actually good things, where there's a new form of cryptography, which is based on lattice, problems on lattices. I worked on this in the early days. But there's sort of a breakthrough by Vinod Vaikutanathan, Zvika Brakersky, and Gentry, Craig Gentry. The first paper was by Gentry. The result is a homomorphic encryption scheme, which is a scheme that can compute on encrypted data without decrypting, which is based on lattice problems. Now, why is lattice problems important for quantum? Because we don't have any algorithm for breaking cryptography based on these lattice problems. Any quantum algorithm, and of course any classical algorithm. So whereas we know how to factor integers in theory on a quantum computer, we do not know how to solve these lattice problems. And therefore all of these crypto systems, the fully homomorphic encryption, and many other systems afterwards, functional encryption, which is incredible invention, attribute-based encryption, they're all based on lattice problems. Or they can be based on lattice problems. So today, there is actually a substitute for the crypto systems that are broken by quantum algorithms. Not only there's a substitute in some theory papers, but there was a call by the National Institute of Standards, by NIST, to propose a post-quantum cryptography for encryption and for digital signatures, and there have been many proposals. They selected, I think, 3. I think 2 of them were based on lattices, 1 wasn't, and that was broken. So now the only existing proposals are based on lattice theory. But there are proposals out there. But why did I say that quantum might be better than classical? Not just because we have a substitute, because a substitute is not better, it's just different. But there are some things that can be done if there are quantum computers that we don't know how to do classically. And one of them is this deniable encryption, which I will speak about actually later today, where there a paper that shows that you can actually get stronger properties if there's the ability of doing quantum computing for an encryption scheme, which we couldn't have done, in fact, provably classically. So something about the nature of quantum computation enables things which are impossible classically. So in some imaginary world, which I don't know when we're going to get to, this post-quantum world, I think that in the ultimate post-quantum world, we're going to do better rather than worse.
Right. So the other very active area of research in computer science today is ML. And for a lot of people, ML is almost synonymous with computer science. Now, how do we think about the influence of ML in computer science, and how do you think cryptographers should evolve their research to address this influence of ML in all of computer science?
So I want to kind of refer to the first thing you said, that for some people ML is synonymous with computer science. It's not. So computer science is a field that has made what we are doing today is possible. The internet, communicate, electronic commerce, database, data structures, systems research, architecture, operating systems, distributed content, search. All of this is not machine learning.
Yeah.
Machine learning is a dream that for many years people had in AI. And in the last 5-7 years, it all of a sudden seems that, for example, neural nets, things that people have thought about. It seemed that because of the availability of data and the availability of large compute, these imaginary dreams, in some sense, the neural nets are the right way to go, seem to have delivered things that people didn't think possible, in terms of vision and natural language understanding. And that is incredible. It all is possible because we have large compute, because we have
Lots of data.
we have data science. We know how to also harvest the data and clean the data in order to deliver it to a machine learning apparatus. Okay, so and also it's 100% clear to me that what is machine learning today is not going to be what it is 10 years from now. In the sense that it will become better, it will be better understood, there will be proofs, there will be a lot more algorithmic methods together with this just magic harvesting data.
Yeah.
So I think it's very important to understand that this is not, computer science has not been overridden by machine learning. Having said that, it's pretty remarkable what these systems can provide. Now, in terms of what cryptography can do for machine learning, or what's the role of cryptography, which I think was the second part of your question, is, again, cryptography really is a way, if you generalize, it's a way to take technology which is not trusted. So if you think about a channel that I can send you a message, but there are adversaries listening on the line, or if you think about even email, there's a lot of people who are spamming me, or documents that are signed digitally. Maybe somebody's just forging the digital signature of mine. It's a lot of, what cryptography does is enables you to sort of trust the channel that I'm communicating, that somebody eavesdropping is not going to be able to understand my messages. Right. Maybe trust that the document